Okay, so the question was to figure out what the packing parameters were for these three geometries, and the answers are kind of very, in a flashy manner, are given here. Yeah. So, although the screen cuts that off, but hopefully it'll be on the. But so for the sphere, it should be a third. So you have the volume of a sphere, 4/3 pi r to the power 3. The area of a sphere is 4 pi r squared, and the characteristic length then that link it all together is the radius of the sphere. So if you put that in, you get 1/3. Now the cylinder, the volume of a cylinder is the area of the circular base, which is pi r to the power 2, and then times the height, which is L in this case, of the cylinder. So then you'll get like the total area of this cylinder would be, you know, the area of the two circles at the top and the bottom, so that would be 2 times pi r to the power 2, plus the circumference times the length, because you roll it out. That's the area, the outer area. So that's 2 times pi times r times L. And again, the characteristic length would be the radius of the cylinder. So what you can do, if this cylinder becomes infinitely long, is effectively just ignore the top and the bottom area of the end bits, really, and then you'll end up with a number 1/2. For the lamellar, you basically have an undefined length 1 and a length 2, and the thickness is 2 times r, which is the diameter of this particular thing. So that will be the volume. You do the same trick with the top area and the bottom area. It's 2 times L1 times L2, and then you'll have these the side areas basically, which you can ignore, and the characteristic length is half the length of this lamellar. So in that particular case, you'll end up with number 1, which for some reason dropped off the screen, but hopefully hasn't dropped off the slide in YouTube. So the interesting thing is now, so this is just geometry. Yeah, so you might think, what has this got to do with molecules that self-assemble or particles that self-assemble? Well, the interesting thing is you can define a packing parameter for a particular object. So you can pick a molecule, for example, your SDS molecule, and you can put the numbers in. So you have the SDS molecule that you pull out, and you can roughly calculate what the volume is, because you know the dimensions. The cross-sectional area would be, you know, maybe the size of the head group, the sulfate head group, which you can figure out how that spaces, and the characteristic length would be this length of this C12 chain in case of SDS. And then you put those numbers in and then see where it works. Yeah, so here you see an example for this SDS micelle. So the aggregation number which people measured was like 74. We've seen this slide before, I think. So you had this packing parameter in there, and you can put just the numbers of the volume. There's a expression for that, and for the length there's an expression for that. And if you put those numbers in, you can figure out what the packing parameter is. So if you would do this with respect well, if you would assume that it's a spherical structure, you can work out that the characteristic length, so if you do the inverse, should be 1.84 nanometer. And if you use the equation from the slide before, if you fully stretch the C12 chain, you will see that it's only 1.67 is the maximum amount that you could stretch it. So your structure should be slightly bigger than it actually is, which is not possible, which means that this thing is a little bit of an egg. Yeah? So an SDS micelle, not necessarily is a sphere. It could be a bit eggy. And obviously, the easiest way to change this is the cross-sectional area. Because with your charge, those charges repel each other. So if you add a little bit of salt or something, then you might be able to pack these things closer, and then you can influence your packing parameter a little bit. And obviously, if you would think about this a little bit more crazy, so if you would change your solvent, then you can change your packing parameters, right? Because it depends on how the system would phase separate. So the volume actually, you could almost say the volume is the part of the bit that does phase separate. So it's the hydrophobic bit, in case if you look at water. And the area would be like, what if I would look at the total area of the object if I go from hydrophilic to hydrophobic? what's the spacing of the molecules then, and what's the effective area on that surface, that gets taken up, so that would be A, and the characteristic length would be then the length of the hydrophobic part. And then you can figure it out whether this would make sense or not. And it's a very useful tool. Okay, so here you see an example. People have played with this. So here you have this is a paper from Science from about 9 years ago. And what they've done, they made a block copolymer in this case, which was very clever for several reasons. So they polymerized butadiene, and then the other block would be ethylene oxide. So clearly ethylene oxide dissolves really well in water, and butadiene doesn't. And the nice thing of butadiene is that the glass transition temperature is really low. So the system is really flexible, which means it's quite dynamic, which means you could change structures. And what you see, if you basically look at this plot over here, you see on the x-axis is the weight fraction of polyethylene oxide relative to the amount in the chain. And then on the y-axis is basically the number of polybutadiene units in a way. So what you basically see is that if I'm high in amount of polyethylene oxide, so relatively the amount of polyethylene oxide is really long, I will make spherical micelles. And that makes sense, because if this polyethylene chain is long, yeah, it wiggles about a lot, and it takes quite a lot of space, which means that A in my packing parameter becomes a large number relative to volume and length, yeah? So if I now just make that bit shorter and shorter, so I go to the left, basically, I should basically up my packing parameter. So I go from values that are less than a third to a half and eventually to 1, which means that my assembled structures should change from spherical micelles to slightly eggy things, elongate into cylinders, and then in the end will form bilayer sheets or vesicles. And that's exactly what you see. So by playing with the relative block length of these things, you can tailor what type of structure you're going to get. That's really important because these three different objects, for example, have got completely different properties by themselves, because obviously they look different. So for example, the vesicle can contain water, and in a way you've got a membrane and there's an enclosed volume in it. The cylinder is very interesting because cylinder is like spaghetti chains, and they can overlap. So you can imagine that cylindrical or worm-like systems will have a very high bulk viscosity. And then the tiny micelles have a, well, relatively high surface area with the water phase. Yeah, and for that reason, they could become an interesting type of aggregate as well. So people are exploring all these different types of self-assembled structures for a variety of applications. So here you see if this weight fraction of polyethylene oxide is 0.34, and this is cryo-chem images, so you see that we're not just stuck to just cylinders, vesicles, and micelles. You have a lot of transitions in between, and you can get all kinds of wonderful shapes, and you can have, you know, that you can ever imagine. So, and these shapes can even be dynamic. So if they're not kinetically frozen, so if the building block, so the molecule, is soluble to a relative extent in the continuous phase, then these things can just exchange shape. So this, like, they're quite dynamic blobs in a way. And as a result of that, if you change the stuff, it takes some time for the new system to reach equilibrium, so to speak. So here, for example, you know, with turbidity measurements, so turbidity, in a way, just measures, well, what does turbidity measure? So turbidity, you can do it with UV vis, right? So you whack some light through a sample, and turbidity means it gets cloudy. Why does it get cloudy? Why do stuff, what's the reason that for a certain wavelength, a solution, well, solution is the wrong word then, a dispersion would get cloudy? Anybody? It's a difference in refractive index, right? If you have a difference in refractive index, you get scattering, depending on how large the aggregates are, so it's wavelength dependent, and as a result of that, you'll get turbidity. Yeah? And what you can see is that, you know, if you change the amount of water in the system, that it takes some time for the system to adjust. So I have a certain system that's stable. I add a little bit of water in this case, and the system just takes time to redistribute. And it depends on the dynamics. So for these molecules, you have to wait about 10-15 minutes before you reach the next state. For SDS molecules, which are way smaller, you can imagine that that goes way quicker. Yeah? So the equilibrium structure, in a way, is a function of lots of things. It's a function of what does your molecule look like related to the packing parameter. And the packing parameter then, in a way, is like how hydrophilic to hydrophobic is this with respect to the solvent. So if you change the solvent, you can go through a different system. And then, you know, concentration also plays a role, because if I have a vesicle or a micelle and I infinitely dilute it, I drop below my saturation concentration and I'll just end up with unimers. Yeah? And then there are some tricks that you, if you want to preserve the structure, what you have to do. So, okay, so this is like something that people love, right? And this is now relatively, well, 9 years old, so you could say it's old. Yeah? Maybe not, because that makes me very old. So, so people have been playing, they say, oh, these micelles, they're great, because I have a hydrophobic core and a hydrophilic outer layer, and then I can put drug particles in the core. And I can inject this in someone's body, and then the biologist loves their endocytosis, and then all these things goes nicely in your cell, and you release the drug, so it's a drug-releasing vehicle. And then you go, well, okay, hang on, wait a minute. There's a few side issues there, right? So for the body not to recognize the thing that you inject, it has to mask itself for the environment. So, for example, polyethylene oxide is relatively good at this. So polyethylene oxide change in water looks like water for outside bodies. So your body is not going to attack this. So it's relatively, you know, kind of inert. So that would be a good hydrophilic outside. If I would take, for example, a polycation as the outside, it'll stick to everything. And everything, you know, it's pretty good antimicrobial. So it's not so very good for your body. Yeah, you get all kinds of side effects. So it depends what hydrophilic bit you pick. And then you say, okay, I'm going to put a drug in there. Now, most drugs are crystalline. Most pharmaceutical drugs are crystalline compounds. And then you have a big problem, right? So you make a little micelle, you put your little drug in there, and then what happens is that your drug, over time, just Ostwald ripens out of the storage jar. So if you have it in the jar, yeah, always thermodynamics is always there. So you have the drug in the micelle, but you also have a tiny little bit of drug in the water. Temperature fluctuations, the water phase oversaturates a little bit. As a result of that, you could get crystal formation in the water that sucks empty basically everything in the micelle. So end result would be a lot of large crystals of your drug on the side of your storage bottle. Now, that's not very practical anymore. Yeah? So you need to find a more creative solution than that. And it's a big problem because shelf life stability, as in basically if you make a medicinal compound or a personal care compound, personal care products needs to be 2 years, 3 years on the shelf. Yeah? And for kind of drug delivery type of purposes, a few months. So if, you know, and this happens in a few days. So that wouldn't be practical. So you need to come up with a solution. How could you do that? For example, covalently bind your drug to the hydrophobic part and then use some clever chemical reaction to get basically unlock it so that it can be released only when it has to be released. Now, the other problem with it was the dilution, right? If you have a micellar dispersion, and if I dilute it in an infinite pool of water, it becomes just separate blocks, and there is no micelle left. So that's another thing that you need to address. So maybe a micelle is a really bad idea overall. So one way to address this is, for example, to cross-link your individual chains together. So once they're formed, they can't disintegrate anymore. And that's done quite a lot. So let's look at two of these things, right? So this is I think it's the similar paper, but I just, instead of a drug, let's just replace it with a fluorescent label. And all I want to say here is that in this particular case, you have polyethylene oxide as the hydrophilic part and polycaprolactone, which is a polyester, so it's biodegradable at least, as the hydrophobic part. And then they covalently lock this group to the end group, which basically means it can't dissolve or Oswald ripen out if it's crystalline. Yeah? So that would work really well. So then you'll have a label which is fixed, and then you have your micelle, but then you still have the problem that if you dilute this, that it might disintegrate. Yeah? Unless it's kinetically frozen. What do I mean with kinetically frozen? That is, if the glass transition temperature of your hydrophobic part is really high, then you basically lock it because it's like a solid then. And then obviously dissolving it might become a bit of a problem. So you could physically say, I'm going to make a hydrophobic part with a really high TG, and then it's physically locked. Or you can say, I'm going to chemically cross-link it. So here you see some nice work, and a lot of people do this nowadays, but it kind of started, I think, by Karen Woolley, and Rachel O'Reilly's group is making a lot of these type of structures as well. And so basically what you get is that they make these micelles, and then in this case, they cross-link the shell. So obviously you have two options. You can cross-link the core, or you can cross-link the shell. So either the hydrophobic part or the hydrophilic part. So, and then you kind of get a jelly object that can't disintegrate anymore if you dilute it. So, so that's in a way the plan, right? So you can make an amphiphilic dye block, you assembled it into a polymer micelle, then you cross-link the shell, and then maybe you can even degrade the core out, and then you have a hollow, well, you can call it a hollow nanocage, kind of a jelly, kind of hydrophilic jelly mess that idealistic looks a bit like that, but obviously if it's jelly, it can wobble around, yeah? So it can have all kinds of distorted shapes. So this looks a little bit small, so but this is one of the examples of how you could do this. So in this particular case, they do a ring opening polymerization to make this caprolactam, and then so that's the hydrophobic part, and then they have one group that they basically modify into a tertiary bromide group, and then as a result of that, you can turn it into a block copolymer, which they've done basically with a tertiary butyl group as protection. Then you basically get rid of the tertiary butyl group, so now you have your hydrophobic part and your polyacrylic acid in this case now as hydrophilic part, and then a polyacrylic acid. An acid you can react in this particular case with an amine in order to turn it into an amide, and therefore you need to do a coupling reaction. So you have this kind of coupling agent that's water soluble that makes that reaction work really well, and then you've got a shell cross-linked shell. And then this polyester, which was the hydrophobic part, can be degraded out. So then you'll have your cage-like hollow nanostructure. Yeah? So that's, and you just have to be creative with your organic chemistry and polymer chemistry to make these kind of things. Okay, so here we saw a little bit already that, if you change the structure of your block, so if you make in this case, the polybutadiene or the hydrogenated polybutadiene between 1 and 2 a little bit longer, then you can go to cylinders or worms. Now in the top case, it's very interesting because you have got a pendant vinyl group left. So once you've made your worms, you can all chemically cross-link them together. Yeah? And then you have permanent worms. Spaghetti, basically. So and this is actually done before. See, in like 1999, so this shell cross-linked micelles, this is like, 4 years earlier than that other paper. So what do you get? Well, here's what it looks like under a TEM image. So you have these wormy structures, and you can imagine that viscosity of this system will be very high. Yeah. So, and obviously, if you've glued it all together, you might even have a gel, a permanent gel. Because this case on the left, you can exchange, right? Things can move, which means you can break up. So your cylinders can snap and make another one. And on the right-hand side, when it's all glued together, the only way how you can break a cylinder is just literally break the covalent bonds, which happens at well under very high shear, but you know. So, and then, you know, people do all kinds of stuff. So here is a bit more biological. So you have an aliphatic, a bit more natural component, and you'll just add, you know, you just add these amino acids together. So a first section will have some pendant sulfide groups, which actually you could covalently link if you want to in the middle section. And the outer section in this particular case has got both phosphate charges and amine charges. Yeah? And then these molecules should look like, what can I do? And basically in this particular molecule, you have some charges and you have some pKa's. So if you vary pH, you can make these things more hydrophilic, which basically turns it maybe into a micellar type of structure, or more hydrophobic, which then ups the packing parameter, which turns it into a gel. So you could make a reversible gel, maybe. So in this particular example here, you see that you get these wormy-like structures under certain conditions, which is, you know, what was expected. And here you see that indeed these things are pH responsive. Well, the picture is a little bit funny because obviously you could just turn it upside down if you take the photo, but I'm sure that they did it, you know, they did it on purpose. So they basically have this sample at high pH, the top left, and then they expose it to HCl vapor. So basically lower the pH, and as a result of that, you can see that the HCl vapor comes in from the top, and you just get gel formation all the way through, which means you can then turn it upside down. And then if you do the reverse, so you expose it to ammonia, then obviously it'll become a system again that you do not have a worm-like structure, which means you don't have a gel. Yeah, so this is a reversible type of simulation, or a reversible type of self-assembly. Then you can get some bizarre things, and if you have something bizarre, you can just publish it in Science. So this is bizarre and fun. So in this case, they have this dendritic structure, and that tends to assemble into these massively long cylindrical objects. And they're huge, because the scale bar in this case is 1 centimeter. So they're like a few millimeters across and a couple of centimeters long. So it takes millions of these molecules in order to make this. So this probably forms a sheet, and then the sheet rolls up, and then you have just a carpet roll, really. And you get structures like this. So they're quite fascinating. Okay, so we've gone from micelles through rods. So the one structure that's left then, which we'll discuss, is vesicles. And there's this, this paper that popularized it. This is again in Science 10 years ago, and they coined it polymer vesicles or polymersomes, which was the larger equivalent of an ordinary type of, you know, vesicle that was known either in biology or synthetically. So what you now have is that you have a bit more playing room, because you can change your blocks of your hydrophilic parts and your hydrophobic parts really easily. So if you keep the ratio the same, so say your total length of your polymer is 10,000, you could also make 100,000. Yeah, keep the ratio the same means that your membrane thickness goes up with a factor of 10. Yeah, which means that an ordinary vesicle typically will have a membrane thickness of 1, 2, maybe 3 nanometer. You can puncture that pretty quickly. Yeah, if you make it 30, 40, 50 nanometer, these things are a little bit more robust. So, and that, you know, that could be quite an interesting object to play with. So, and here you see that these things can be quite nice to play with. So on picture A, you see a twin tail standard type of structure that forms a bilayer or a vesicle type of arrangement. And picture A, you can see that, if you have a swollen object and it's polymeric, then you can basically have a way higher thickness of the hydrophobic part. And as a result of that, you see a giant vesicle here, which you can make, and you can actually take a micropipette and just, well, suck it in, and it doesn't break. So you can actually measure the membrane rigidity and the elasticity of these type of components. And they're very robust, which means that you can deform them, and you can put all kinds of stuff in there, and it stays in there quite nicely. So again, this area has really come up, and you'll find hundreds, if not thousands, of papers on this particular topic in the last, well, I would say the last 15 years. One of the reasons being that block copolymers have become way more widely accessible through living radical polymerization techniques. So such nitroxides, ATRP mediated, and raft. So here you see a few of these structures, but obviously if you're a bit imaginative, you can basically pick any hydrophobic part. So in this case, it's like a styrene unit, and you've got a acrylic acid, or methacrylic or acrylic acid at the top. Here you've got polyethylene oxide sticking out. Yeah, so anything that's hydrophilic, hydrophobic, you can get your hands on. You can make structures that look like that, and then obviously you can influence the properties of these components. Here are a few more. So this is more the biological one. So you only have a CA chain here, so you don't have a very rigid bilayer here. And then in all these kind of cases, you can just take, even via other routes, like so living anionic polymerization, you can make all kinds of structures and vary whatever groups you want wherever. And then again, how do you make these kind of things? Well, because you might wonder, if I have a really large block, and typically the hydrophilic part is about 10% by weight, the hydrophobic block, if you chuck that in water, it just ends up like a blob, and it doesn't do anything. So what are two of the ways there's more ways of doing this. One is a process called electroformation. So what you do is you just paint a conducting glass slide, so ITO, indium tin oxide glass, a slip with your block copolymer. So you'll end up with lamellar sheets there because it will phase separate in the bulk. Then you put water on top of it, and you just jizz it with electricity, and then it starts to bubble, it starts to hydrate. These lamellar sheets kind of pop up, and then they form a big vesicle. So you'll get stuff that's like in the micron range, like 10 microns and above. The other way is you can start with a process which is called non-solvent addition. What you do then is you start with a good solvent for both parts, for example, THF, yeah, and then you just dropwise add water. And what you see then is you go from micelles through rods, and in the end product is a vesicle. And you can get rid of the THF just by evaporation or by dialysis. And then you'll end up with these beautiful pictures here at the bottom, which are a cryo picture of a block of PMMA with ethylene oxide. And they're obviously smaller, submicron. Then the same thing applies, because obviously if you dilute this stuff, it disintegrates. So what you can do is that you can cross-link the system, and you'll see very nicely in this picture here that these things are then, well, very robust. So you have it in water, and then you can even just dunk it in an organic solvent after it's been cross-linked, and it doesn't blow up, so it can withstand quite a big gradient in osmotic pressure, and then you can put it back in water and it just nicely rehydrates again. Even you can just let it dry out in air, and if you put it back in water, it just forms back again. So it's quite a versatile little balloon that you've made, basically. So, and then people start playing with this stuff. So this is one of the earlier things that they actually try to make a synthetic cell, right? So you have these bacteriophages that can absorb all kinds of DNA, and you can make that part of your vesicle, and then obviously you have a vesicle that can absorb a lot of DNA. You can start to make systems then, if you're clever with your chemistry, that disintegrate stuff. So here in this Nature Materials paper, you have a polypropylene sulfide as a hydrophobic block, And the sulfide groups you can oxidize, yeah, so you get SOO, which means it makes it hydrophilic, and then suddenly instead of amphiphilic, you have everything is hydrophilic, which means you go from vesicle type of arrangement to complete disintegration. So you can get triggered release, yeah? Another way of doing that would be just, so this is actually the same example, so you have, but they trigger it here with glucose. So you have these sulfides in the backbone that you oxidize, which makes the backbone more hydrophilic, which basically would rupture the vesicular structure. And you get nice, in this case, nice glucose-based self-destruction. In this example here, you have a bilayer that's made out of two components. So you have one part is packed with polylactic acid, and one part is packed with polycaprolactone, and one of the two components hydrolyzes way quicker than the other one. So you basically start to rupture the stuff, so you get a permeable vesicle system, and then stuff can disintegrate, and you can get gradual or controlled release, depending on your condition. So you can do this enzymatic, or you can just do this via a pH trigger. Now, last slide. Obviously, at work, a lot of people are playing with this. We play with it a lot, and we've explained the stuff on the left already. But Rachel O'Reilly group plays even more with it. So she makes a lot of micellar and vesicle types of structures. And so this is one of her examples. So she had a really nice hydrophilic, hydrophobic tri-block with a metal in the middle of the hydrophobic block. So, and what you get then, if this stuff self-assembles, she could specifically even remove one of the hydrophobic parts. So you'll have a hollow nanocage in which the inside is basically labeled with little metal ions. So, you know, if you're a bit creative in your chemistry, you can make all kinds of wonderful structures. So, okay guys, that's it for today.